Hello students, welcome back to the class. Today we are going to begin a new lesson. The name of the lesson is nothing but three-dimensional geometry. In this lesson we are going to find how we can represent various things on a space, or how we can represent the line or the equation of a line or equation of 2 points or the angle between the 2 points, etc. in a three-dimensional plane or in space. Suppose that we want to locate a point on a paper. It is easy for us to do so because we know what is a two-dimensional plane. We can draw x-axis and y-axis in the paper itself, and we can easily locate the point by using the x and y coordinate system, right? In the three-dimensional geometry, we are going to locate anything which is on a space. That is possible by using the three-dimensional coordinate system. Here we are using the x-axis, y-axis and z-axis. It is easily observable for you, the three axes from your day-to-day life. Just observe the corner of your room. It just looks like an x-axis, a y-axis and an z-axis. So you can easily spot or locate anything in the entire room, right? So in this chapter we are going to discuss some interesting facts about three-dimensional geometry as well as the three-dimensional space. We also going to derive the equations of various quantities like a line, a point, a line connecting 2 points, a segment of line in this chapter, and so we are going to find the angle between two lines and the magnitude of two lines and etc. in this chapter. So stay tuned and we shall begin this session by a already known concept, which is directional cosines. We learned what is direction cosines, right? We know that whenever we are provided with a vector, we learnt direction cosines in vector, right? Whenever we are provided with a three coordinate system, that is, if this is x-axis and this is y-axis and suppose this is nothing but z-axis, then we learned that if we are provided with such a coordinate system, we can locate any point just like this. And we said that we can find the position vector of the point and the origin just like this. And then we said that the angle made by the vector with respect to x-axis is nothing but alpha, and the angle made by the vector with respect to the y-axis is nothing but beta, and the angle made by the vector with respect to the z-axis is nothing but gamma. Then we defined cos alpha, cos beta and cos gamma are the directional cosine or direction cosines, because it shows the direction as well as the position of the position of the vector with respect to the 3D plane. 3D plane means three dimension. We have an x dimension here, a y dimension here and an z dimension here. So we call this plane or this system as a 3D plane or 3D geometry, because we are going to define various geometrical shapes in this 3D plane. Now cos alpha, cos beta, cos gamma are nothing but the direction cosines. Now we know that cos alpha, cos beta, cos gamma respectively are the direction cosines of the vector, say vector A, right? Now we are going to denote this direction cosines in a special notation. Always remember that cos alpha, cos beta, cos gamma are the direction cosines, whereas alpha, beta, gamma are respectively the angles made by the vector with the x-axis, y-axis and z-axis. Now we are going to notate cos alpha by the letter L and cos beta by the letter M and cos gamma by the letter N throughout this chapter. So throughout this chapter, the letter L means it is the direction cosine where it is cos alpha, and it is where the angle alpha means the angle made by the vector with respect to the x-axis, and cos beta equal to M. Then M means M is nothing but cos beta, where beta is the angle made by the vector with respect to the y-axis, and the notation N means it is the direction cosine where cos gamma, where gamma is the angle made by the vector with respect to the z-axis. So we have L, M and N are the direction cosines now, right? In vector algebra, we learned that cos alpha is nothing but A by mod A. Sorry, A1 by mod A if vector A is this is vector, if this is vector A, then and we define vector A is nothing but A1 I cap plus A2 j cap plus A3 k cap. Then by this result, by this definition, we have cos alpha is nothing but A1 by mod A, cos beta is nothing but A2 by mod A, and cos gamma is equal to A3 by mod A. We learned this thing in vector algebra. If you have doubt in these cases, just go back to the section of vector algebra dealing with direction cosines. Okay. So cos alpha is equal to A1 by mod A, cos beta is equal to A2 by mod A, and cos gamma is equal to A3 by mod A. Instead of cos alpha, cos beta, cos gamma, we can use the new notations, that is L, M and N. Right. Now I am going to find L square plus M square plus N square. It is equal to, what is L square? A1 square divided by mod A square plus what is M square? A2 square divided by mod A square, and finally what is N square? It is nothing but A3 square divided by mod A square, right? See, mod A square is common for all fractions. So we have it is equal to A1 square plus A2 square plus A3 square whole divided by mod A square, right? Now look at this, A1 square plus A2 square plus A3 square. What are A1, A2 and A3? A1 is the first component of the vector A, A2 is the second component of the vector A, and A3 is the third component of the vector A, right? So we have mod A is nothing but square root of A1 square plus A2 square plus A3 square, isn't it? That means mod A square is nothing but we can take off the square root, then it will become A1 square plus A2 square plus A3 square, right? We can substitute this here, it will become mod A square whole divided by mod A square, which is equal to 1. Which means that the sum of the direction cosines is nothing but 1. So L square plus M square plus N square is equal to 1. So this is our first result in this chapter. Relationship between the direction cosines are nothing but the sum of the squares is nothing but 1. So L square plus M square plus N square is nothing but 1. Now we shall discuss some more important properties or things that we want to know before entering into the chapter. Now we know that since L is equal to A1 by mod A, M is equal to A2 by mod A, and N is equal to A3 by mod A, we can easily represent L is equal to KA1, M is equal to KA2, and N is equal to KA3. Nothing happened here, actually K is nothing but 1 by mod A. So we can represent, for the convenience of other derivation, we just represent 1 by mod A as our K. So we have L is equal to KA1, M is equal to KA2, and N is equal to KA3. Then we know that L square plus M square plus N square is equal to 1, right? So we have it is equal to KA1 the whole square plus KA2 the whole square plus KA3 the whole square is equal to 1, which means that K square A square plus K square A2 square, sorry that is A1 square, plus K square A3 square is equal to 1, which means that K square into A1 square plus A2 square plus A3 square is equal to 1, which implies K is equal to 1 by A1 square plus A2 square plus A3 square. So sorry, K square is equal to, so K is equal to plus or minus 1 by square root of A1 square plus A2 square plus A3 square. See, we just chose the plus or minus symbol that just to show that whenever we are changing the direction of the measurement of the angle, that is, if we take anti-clockwise direction as the measurement of angle positive, then clockwise measurement of the angle will be negative. So the sign will be reversed. So just to show that change in the sign, we just put a plus or minus here. So we have L is nothing but KA1, that is plus or minus A1 divided by square root of A1 square plus A2 square plus A3 square. M is equal to plus or minus, what is M? KA2. So plus or minus A2 divided by square root of A1 square plus A2 square plus A3 square, and finally N is equal to plus or minus A3 divided by square root of A1 square plus A2 square plus A3 square, since M is nothing but KA3. K is nothing but plus or minus this. So N is equal to KA3. So K is nothing but this. So plus or minus K into, what is K plus or minus this, into A3. So we have N is equal to A3 divided by square root of this. So why we derived this relationship? Just to show that whenever we are given with a vector, say suppose we are given with A1 I cap plus A2 j cap plus A3 k cap, then we can easily derive the direction cosines as L is equal to plus or minus A1 divided by square root of A1 square plus A2 square plus A3 square. M is equal to plus or minus A2 divided by square root of A1 square plus A2 square plus A3 square, and finally N is equal to A3 divided by square root of A1 square plus A2 square plus A3 square, because we are provided with the vector A is equal to this, and we know what is A1, A2 and A3. So it is enough for us to just substitute those values of A1, A2 and A3 in each of these equations to get L, M and N. So whenever you are asked to find the direction cosines from such a format, it is simple. Just substitute the values of A1, A2 and A3 in these equations, plus or minus. We just denoted this sign in order to show the direction cosines can be either be negative or be positive according as the direction of measurement of the angle. If it is anti-clockwise, the direction cosines will be automatically positive, and if it is clockwise, the direction cosine will be negative of sign. So it is just a matter of showing the direction of the measurement of angle. And we can easily evaluate any direction cosines using this formula. Also note that if A, B, C are the direction ratios of a line or a vector. The directed line segment is called a vector, so that's it. So if A, B, C are the direction ratios of a line, we know that for any scalar not equal to 0, Ka, Kb and Kc are also the direction ratios of the same line, right? We learned this in our chapter vectors. So if ABC are the direction ratios of a line, then is scalar, if K is a scalar, then the direction ratios multiplied by the scalars are also the direction ratios of the same line. Then we can say that whenever two direction ratios are of the same line, then they must be proportional. That is, if ABC are the direction ratios of a line, the other direction ratios of the same line are of the form Ka, Kb and Kc, which means the direction ratios of a line are always proportional. The respective direction ratios of a line are always proportional. That is, A and Ka are always proportional, B and Kb are always proportional, C and Kc are always proportional. Suppose that 2, 3 and 5 are the direction ratios of a line. Then we can find another set of direction ratios of the same line. Just find a set of direction ratios which is proportional to this. Suppose I am finding 4, 6 and 10. Each direction ratio is multiplied by 2. See, this set is also a direction ratio for the same line. Also we can generate lot more direction ratios just like this. Suppose I can find a new set like 8, 12, 20. See, each of these direction ratio is multiplied by 4 to get the new direction ratio, which is also the direction ratio of the same line, which means that the direction ratios of a line are always proportional. And it also means that a single line can have infinitely many direction ratios. Infinitely many set of direction ratios. See, this is a set of direction ratios for a line, and this is another set of direction ratio for the same line, and this is also another set of direction ratio for the same line, which means that a line can have infinitely many set of direction ratios. Always note that the scalar k must be not equal to 0. So whenever we are provided with a line, we can easily find infinitely many direction ratios for the same line. What all things we need to remember is, just remember that always the direction ratios must be proportional, or the respective components of the direction ratios must be proportional. If the respective components of the direction ratios are proportional, we can say that each set of direction ratios represent the same line. So we shall move on to the next topic. Now the next session is direction cosines of a line passing through 2 points. We know that whenever we are provided with only 2 points, we can always draw a single line through those 2 points, right? Suppose that I am provided with 2 points, say P and Q, on the 3D plane, right? Now I am going to draw a line which passes through these 2 points just like this. So this is the line PQ, which is obtained by drawing or connecting the points P and Q. Now observe this picture well. I have to find the direction cosines of this line. For that, I am drawing a perpendicular from P as well as to Q, as well as from Q to the plane XY plane. See, this is the XY plane. This is a plane, and this plane is called XY plane, since we only marked X and Y axis here. Z axis is absent here. So I am going to draw perpendicular from P to the XY plane and Q to the XY plane. This is just a construction in order to find the direction cosines of the line passing through P and Q. So I obtained a figure like this, right? Now I am going to draw a perpendicular from P to Q, P to this line, to meet at N. So this is Pn and this is a perpendicular. Let us mark this as R and S. So what I have done is just drawn perpendiculars from P to the XY plane to reach at the point R, and drawn a perpendicular from Q to S to reach at the point S. So we get QS and PR are the two perpendiculars. Now I drawn a perpendicular from P to the line QS to get PN. So this is it. Now just observe that if I extend this line, I got a directed line like this, right? Now the angle gamma is the angle made by the line with respect to the Z axis, right? Since this axis and this line, this perpendicular, are parallel to each other, this line PQ, extended line, we can name this as O. So the extended line OQ behaves as a transversal, and this line will also be equal to gamma, since it is alternate interior angles. So we get this as gamma and this as gamma. So we have to find cos gamma, because if gamma is the angle made by the line or vector with respect to the Z axis, then the corresponding direction cosine is nothing but cos gamma. Now let us elaborate for convenience. Let me just draw this triangle into a bigger picture. So just observe this. P, Q, N, and this angle is gamma. So now you can see this is the enlarged version of this small triangle, right? From this we can easily find cos gamma. Now just observe, cos gamma is nothing but opposite adjacent side, which is NQ, by hypotenuse, which is PQ. So NQ by PQ is nothing but cos gamma, right? Now observe that P is the point, let P is the point x1, y1, z1, and Q is the point x2, y2, z2. Let P and Q be 3 points. So 2 points. We are giving 3 coordinates because the points are in the 3D plane, right? So we have P is x1, y1, z1, Q is x2, y2, z2. always observe that NQ is the line. See, NQ is the line which is perpendicular to the XY plane. So the coordinates x2 and y2 will be the same for the point N also. But Z2 will vary. What will be the change in Z2 here? Z1 will be the third coordinate of this point, because we know that whenever we draw a straight line or a perpendicular line in the two-dimensional plane, see, all these points in the same line have the same x coordinate, but the y coordinate keeps on varying, which means that if we draw the NQ is a line perpendicular to the xy plane, means that here the coordinate x2, y2 will be the same for N also, but the change happens to the third coordinate, which is Z1. So NQ is nothing but, N is nothing but x2, y2, Z1. So we have cos gamma is equal to NQ by PQ, and NQ is nothing but what? X2 minus x2 is 0, y2 minus y2 is 0. So what is balance is nothing but Z2 minus Z1 divided by PQ. Actually observe that NQ is equal to square root of x2 minus x1 the whole square plus y2 minus y1 the whole square plus Z2 minus Z1 the whole square. See, x2 minus x1 here, so first coordinate and second coordinates are the same. So x2 minus x2 is equal to 0, y2 minus y2 is equal to 0, and what remains, the rest is root of Z2 minus Z1 the whole square, which is nothing but Z2 minus Z1. So we have NQ is nothing but Z2 minus Z1 divided by PQ. Now cos gamma is obtained as Z2 minus Z1 by PQ, right? Similarly, cos alpha can be obtained as x2 minus x1 divided by PQ, and cos beta is nothing but y2 minus y1 divided by PQ. All these have the same kind of derivation, just like this. You not need to remember all these derivation step. Just remember the final result. Cos gamma is equal to Z2 minus Z1 by PQ. Cos alpha is equal to x2 minus x1 by PQ, and cos gamma is equal to y2 minus y1 by PQ. Now we shall just list out all these result all together, just like this. Cos alpha is equal to x2 minus x1 divided by PQ. Cos gamma is equal to y2 minus, cos beta is equal to y2 minus y1 by PQ, and at the last cos gamma is equal to Z2 minus Z1 by PQ. What is PQ? PQ is nothing but the distance between P and Q, that is PQ is equal, we know that PQ is equal to square root of x2 minus x1 the whole square plus y2 minus y1 the whole square and plus Z2 minus Z1 the whole square. So whenever we are given with 2 points x1, y1, Z1 and x2, y2, Z2, and we are asked to find the direction cosines of the line passing through these 2 points, it's very easy. Just find PQ, and first you have to find PQ, that is root of this, and cos alpha is nothing but x2 minus x1 by PQ. Cos beta is nothing but y2 minus y1 by PQ, and cos gamma is nothing but Z2 minus Z1 by PQ. Always remember this result. The derivation is just for the conceptual purpose. You just understand the method we derived or we reached at this final stage, and just forgot all these things. Just remember, just by heart the formula in the end, so that you can do the problems very easily. Now we can move on to some problems regarding this session. Now we shall discuss the examples. Example 1. If a line makes angle 90 degree, 60 degree and 30 degree with the positive direction of x, y and z axis respectively, find the direction cosines. So we are given with alpha is equal to 90 degree. We know that alpha is the angle made by the line segment with respect to the positive direction of x axis. Beta is equal to 60 degree and gamma is equal to 30 degree, right? So we have to find the direction cosines. It's very easy to you. The direction cosines are cos alpha, cos beta and cos gamma, right? Cos alpha is nothing but cos 90 degree, which is equal to 0. Cos beta is nothing but cos 60 degree, which is equal to 1 by 2. Cos gamma is nothing but cos 30 degree, which is equal to root 3 by 2. It is as simple as that. Now we shall move to the second example of your textbook. Coming on to the second example, the example is that if a line has direction ratios 2, -1, -2, determine its direction cosines. We know that whenever we are given with the direction ratios, let the direction ratios be A, B, C, then the direction cosines is given by the formula A by root of A square plus B square plus C square, B divided by square root of A square plus B square plus C square, C by square root of A square plus B square plus C square, right? Now we can easily find here A is equal to, what is the first point? 2, B is equal to -1 and C is equal to -2. So we can have direction cosines. See, DCs means direction cosines is equal to 2 divided by square root of 2 square plus 1 square plus 2 square. Actually -1 square. -1 square is actually same as to 1 square. -2 square is again same as to 2 square. That's why I written plus 1 square plus 2 square. And next one is B. B is -1 divided by square root of again 2 square plus 1 square plus 2 square. And the third one is C. C is nothing but -2. -2 divided by square root of 2 square plus 1 square plus 2 square. And it is equal to 2 by, what is square root of 2 square plus 1 square plus 2 square? It is 4 plus 4 plus 1. It is 9. That is root 9 is equal to 3. 2 by 3 minus 1 by 3 minus 2 by 3 are the respective direction ratios of the line. You can generate direction cosines of the line. So in the same way you can find the direction cosines of any line segment if you are given with the direction ratios A, B, C. Just apply the formula. We shall move to the third example. Now coming on to the example 3, find the direction cosines of the line passing through the 2 points. We are given with 2 triplets, -2, 4, -5. The next point is 1, 2, 3. See, this is nothing but x1, y1, z1. This is x2, y2, z2. We know that whenever we are given with 2 points x1, y1, z1 and x2, y2, z2, the direction cosines are, the direction cosines are what? x2 minus x1 divided by pq. Suppose that this point is p and this point is q. And next one is y2 minus y1 divided by pq. And the third one is z2 minus z1 divided by pq, right? Now we can easily find pq as square root of x2 minus x1 the whole square. Here x2 is 1, x1 is -2. So 1 minus -2 the whole square plus y2, 2 minus 4 the whole square, 2 minus 4 the whole square plus, and the last component 3 minus -5. So 3 minus -5 the whole square, which is equal to square root of 1 plus 2, 3 square, 9 plus 2 minus 4, -2 into square, 4 plus 3 plus 5, 8 square. That's it. So this is equal to 64 plus 4 is equal to 68 plus 9 is equal to 77. So root 77. So we have direction cosines. First direction cosine is nothing but L, second one is M, and third one is N. Cos alpha, cos beta, cos gamma. So it is nothing but x2 minus x1. That is 1 minus -2. So 3 by root 77. And the next one is y2 minus y1. That is 2 minus 4 minus 2 by root 77. And the last one is z2 minus z1. 3 minus -5. It is 8 by root 77. So we can easily find the direction cosines by just identifying the points x1, y1, z1 and x2, y2, z2 and applying the formula. Always remember this formula also. We shall move to the next example. So coming on to the fourth example, it is find the direction cosines of x-axis, y-axis and z-axis. Always remember that x-axis, y-axis and z-axis are all directed lines. So they can also have direction ratios and direction cosines. So coming on to the direction cosines of x-axis. We know that the direction cosines of x-axis LMN is equal to x-axis makes 0 degree with the positive direction of x-axis. So first direction cosine is cos 0 degree. X-axis makes 90 degree with the positive direction of y-axis. So the second direction cosine is cos 90 degree. Also x-axis makes 90 degree with the positive direction of z-axis also. So then the third one is cos 90 degree. See, you can easily identify this using this picture. See, x-axis, this is x-axis, this is y-axis and this is z-axis. X-axis makes 0 degree with x-axis. X-axis makes 90 degree with y-axis and x-axis makes 90 degree with the z-axis. That's it. So we get this. So that is equal to cos 0 equal to 1, cos 90 is equal to 0, cos 90 is equal to 0 are the respective direction cosines of the x-axis. Similarly, direction cosines of y-axis is simple like the 0, 1, 0, and direction cosines of z-axis is again 0, 0, 1, just like this method. So this is very simple question, but remember these kinds of questions are frequently asking in competitive exams, so just try to focus on this type of questions. The next example is show that the points A is equal to 2, 3, minus 4 and B is equal to 1, minus 2, 3 and C is equal to 3, 8, minus 11 are collinear. So we have to find, or we have to show these 3 points are collinear, which means that these 3 points lies on the same line. First of all, it is easy for us to find the direction ratios of lines AB and direction ratios of BC. Suppose that this is A, B, C. So we can easily find the direction ratios of AB and direction ratios of BC. Just like we done in the chapter vector, we can find AB as 1, minus 2. So the direction ratios of AB is equal to 1, minus 2. First component minus 1, second component minus 2, minus 3, which is minus 5, and the third component 3 minus minus 4, which is 7. So we get the direction ratios of the line AB as minus 1, minus 5, 7. Now the direction ratios of the line BC equal to 3 minus 1, it is equal to 2. 8 minus minus 2, it is equal to 10. Again minus 11 minus 3, it is equal to minus 14. See, we obtained the direction ratios of AB as well as the direction ratios of BC. Just before I told you that we can have infinitely many direction ratios for a single line. Also I told you that whenever we are given with 2 or more direction ratios of a single line, that all the 3 sets or all the 4 sets are proportional. Then only we can say that all the 4 sets are the direction ratios of a single line. See here, minus 1, 2, minus 5, 10. 7 minus 14. See, the direction ratios of AB and BC are proportional. That is, we can obtain the direction ratios of BC just by multiplying each component of this direction ratios of AB by minus 2, right? Minus 2 into minus 1 equal to 2. Minus 2 into minus 5 equal to 10. Minus 2 into 7 is equal to minus 14, which means that both these direction ratios are proportional. Hence, we can say that these are the direction ratios of a single line. Also note that B is a point common to both these lines, which means that the points A, B, C are collinear points. So in order to check collinearity using direction ratios, just check whether the direction ratios of the line AB and direction ratios of the line BC are proportional or not. If they are proportional, all the 3 points lies on the same line. If not, no, nothing happens, they are not collinear. So in a way we can define 3D, 3-dimensional geometry. This class was an introduction to to three-dimensional geometry. I hope you understood some of the basic concept in relation with the vector algebra. So we can move further deeper into the next classes. So wait for the next class and study this concept well before you attend the next class. So stay tuned till then. Bye.